Hi everyone, welcome to the Cloud Skills Show this week. You're very welcome. If you haven't watched the Cloud Skills Show, this is a weekly live stream that goes out on Learn TV and Microsoft Developer UK and many other channels. And this week, actually, many of you were watching in the UK or elsewhere in Europe, Middle East, Africa, everywhere, sort of roughly in a time zone where you can watch stuff from the UK, will know that it's actually been an AI Digital Skills Week at Microsoft. And so we've actually had quite a lot of AI content this week. And we started off, in fact, there's been content every single day. But on Tuesday, we did a show called Tech Days, a developer's guide to AI, and that was hosted by the wonderful Amy Boyd. And actually, I was sort of here in the background pushing the buttons and and stuff like that and trying to make it happen. And we had so many wonderful questions from people who were asking about how a developer that maybe isn't using any AI functions today can incorporate that into the product. And so what we looked at, there was quite a bit of things like conversational AI around how to put bots in your application, how to interpret text using some of the pre-built connectors in Microsoft's Cognitive Services Toolkit. And we've also had panels about what the future of AI is, what does that mean for people's jobs, and also what can people expect in the future. But for today's show, we thought that we'd have a look in a bit more depth at machine learning. And so because we've heard from so many people in the UK, actually we thought, let's ask some of our friends overseas. And so we've got the wonderful Ari Bornstein and Tal Barmel with us from Israel. Hi, guys. How's it going?
Hi, Adam. How's it going? And thank you for having us.
It's going very well. As you can see, I've got my fireplace lit. It's cold here. I hope the weather's a little bit better where you are.
Just a little bit.
Just a little bit. Yeah. Okay. Well, I'm glad to hear it. So I thought before, and you and Tal are gonna, really lead today's conversation, and I'm gonna sort of disappear behind the scenes. But before I disappear off for a little while, it'd be great just to get a quick introduction from each of you, hear a little bit about, hey, what do you do? What's your day job? And how did you get into what you're doing today? Shall we start? Let's start with Tal, actually, sure. and we'll hear from you, Ari.
Hi. So I'm the data scientist at the Dynamics 365 Sales Intelligence. I work on a feature called Conversation Intelligence, which is a feature that records the conversation of salespersons and help them understand better what they did good or not as good in the conversation.
That's amazing. And Ari?
Perfect. So I am a senior cloud advocate in the AI and machine learning team, same organization as Adam over here. And my focus is traditionally machine learning, advanced machine learning scenarios on Azure, as well as natural language processing, computer vision, and many other types of interesting things as well. I got started actually in my undergraduate. I took on a project working with Innova healthcare system in Virginia in the United States on document classification. I didn't know much about machine learning at the time. This was about 8 years ago, and discovered the whole world of machine learning as a potential solution to the problem. And from there, through a career in Microsoft, and now as I'm finishing up my research degree at the Bar-Ilan Natural Language Processing Lab, I've learned a lot, and I'm looking forward to sharing it with the community today.
That's amazing. And so before we start today's show, before we get into the main content, we would love to hear some of the questions from you. So wherever you're joining us, if you're joining us on Twitter or Facebook or Twitch or wherever else we are presenting, please do ask your questions in the live chat, and we'll try and pick them up and ask them. And the other thing is, as we go through today's show, I will be bringing some of the content up on the bottom of the screen. It looks a little bit like this. But we won't grab everything right away, and some things always come up in conversation. So what we do is we write down all of the links and resources from the show, and we put them on a web page. And that web page is already live, and you can find actually the profiles of Ari and Tal on there. So that's aka.ms/cs-s2e7. That's series 2, episode 7. And we'll have those updated later today for you. So I'm going to disappear now into the background, but I will be here, and I may be popping up from time to time. But Ari and Tal, love to hear a bit more about some of the work that you've been doing.
Absolutely. So at this point, I'm going to start sharing my screen. Let me get everything set up, and we'll go and get started from there. So, all right, here you see my screen. Today, what we're going to be talking about, I know in the last session, we talked a lot about how, or the last episode, we talked a lot about how, as a developer, you can get started with AI or integrating AI technologies into your applications. And today, we're going to take a little bit of a shift, and we're going to talk to an audience of more from a machine learning developer, a machine learning engineer, how you can optimize your workflow with PyTorchLightning and the Azure Machine Learning Service. So for those of you who might be familiar with deep learning or machine learning and have a background, you might be familiar with PyTorch as a framework for training deep learning models. When you're developing with PyTorch, there's a lot of boilerplate code or a lot of code that gets customized for little tricks and optimizations that we do that gets integrated into our own research code. It makes it kind of hard to scale that code. And so what PyTorchLightning provides is it provides an interface on top of vanilla PyTorch that allows us to better organize our code, and we gain a lot of really powerful features such as distributed training for free, and we'll dig a little bit more into each of these features as the show goes along. I have my co-host Tal here, who, as I go along, he's going to be learning a little bit more about Lightning and AzureML today as well. So as a proxy for the audience, as well as he's learning or has questions or runs into things or is interested, he'll be stopping me and interrupting and asking, and I'll try to address each of these questions so that we can provide a more wide perspective. So let's get started. One of the most complex scenarios when you're training models on Azure or machine learning models is the concept of actually distributing the training of these models. And you can imagine this is kind of a complex scenario because you need to find a way to load your data, to distribute your data across multiple nodes. You need to manage your compute. You need to manage each of these individual processes. And traditionally in Azure, if we wanted to do this, well, we have a lot of this free, easy to use distributed compute through the Azure Machine Learning Service. It can be hard. You still need to do a lot of processing traditionally with libraries like Horovod to distribute your code. And what we're going to show today is how using an interface and a wrapper library like PyTorchLightning, we can actually do all the distributed computing code and train really powerful distributed models without changing a single line of our actual training scripts. So with that, I'll get in a little bit deeper. The model that we're going to train today is we're going to look at the concept of an autoencoder, and we're going to take a vanilla autoencoder. For those of you who might not know, what an autoencoder does is you provide an input. You have a model configuration that tries to encode the input into a tensor or some sort of vector representation. And then what you want to do is you want to have another model called the decoder, and we want to try to reproduce the original image. And then what we can do is we compare what we reproduce to the original, and then we use that loss to update the weights. And the goal here is if we have a model that can generalize our data set and take the inputs and reproduce them, we have a way of reducing our data set into a smaller representation of core features that can be really useful for clustering tasks or input features for all sorts of models. And traditionally, this can be a little bit more of there are many variations of different kinds of autoencoders, and it can be pretty hard to manage in vanilla PyTorch because you're essentially working with two models that you need to combine, one for encoding and one for decoding. And we're going to show today how using PyTorchLightning, and we'll talk about exactly what that is, how we can more easily train these models and add varying complexity to our configurations without having to add additional code. So let's get into each of these things. At this point, we talked a little bit about PyTorchLightning, but some people might be asking, what is PyTorchLightning? So PyTorchLightning is, as we said, a lightweight wrapper for high-performance AI research with PyTorch. It enables maximum flexibility. It abstracts a lot of the unnecessarily boilerplate code in PyTorch, but also unlike frameworks like Keras that also, or FastAI that also abstract, it enables you to override a lot of the hooks. So when you need to go deep, it's fairly easy to go deep on your code as well.
Harry, can you give an example of some of the boilerplate code?
Yes, absolutely. So there's actually on the PyTorchLightning.ai/tutorials, they have these really nice anywhere between 30 seconds to 5-minute tutorials that talk about a lot of the different interesting boilerplate features so things like being able to fine-tune your learning rate, your training loop. And typically when we train a model, we have 3 loops in our optimization. We have a training loop, we have a validation loop, and we have a testing loop. And then we start adding a lot of additional complexity as we go on and try to optimize and add a bunch of little tricks. So for example, if we want to add early stopping to a model, we might add a lot of additional logic. If we want to run our model on a GPU versus a CPU or a TPU, we also have to deal with how do we convert each of our tensors over. And a lot of this boilerplate code is not actually directly related to the actual machine learning task or model configuration. It's more just to make things work. So what PyTorchLightning does is it abstracts this out. Instead of me having, if I have then 2 pieces of code that are already using PyTorchLightning, I don't have to worry about that one piece of code is configured for a TPU with early stopping, and the other one is configured for a GPU and is using 32-bit encoding when my first model was only using a 16-bit precision for my tensors. So a lot of these tricks and things, we get them for free through PyTorchLightning. Makes managing our code much easier. And now let's go back and one of the most important ones that we get when working with Azure Machine Learning, and we'll transition a little bit and talk about Azure Machine Learning, is the concept of distributed training. So one of the really powerful features of PyTorchLightning is once you have a trainer working that runs on one GPU, it's fairly trivial to make that same code run on 2 GPUs, 3 GPUs, or even multiple nodes with multiple GPUs, which traditionally in Azure Machine Learning has been a very challenging process. And now we're going to show today, we're going to go through and we're going to give an advanced example of how we can run 1 GPU, 2 GPUs, and a multi-node cluster. And we'll also show how we can add logging in there for free with MLflow and TensorBoard as well. Does that answer the question, Tal?
Yeah.
Sorry, I'm just going to get a quick drink of water, and then we'll continue. So now that we've talked a lot about Azure, now that we talked a lot about PyTorchLightning, let's talk a little bit about what Azure Machine Learning is and what the Azure Machine Learning provides. So the Azure Machine Learning service is essentially it's a collection of cloud services that help with the management and preparation of data, integration of data from all the other amazing services in Azure like Synapse and Databricks and the like, Cosmos DB, you name it. It enables us to build and experiment and manage the training of models, to track different experiments and configurations across distributed teams, and also deploy models into production, both as single cloud services, as onto Kubernetes clusters, and additionally to directly and manage deployment directly to edge devices. So extremely powerful and versatile service. Let's kind of show exactly how we get started with that. And if you're interested, by the way, there's a lot of great documentation here at docs.microsoft.com, english.us/Azure machine learning. And here we'll go, there's a really nice overview. I'll put the link in the chat at the end. So let's, one last thing before we start digging in too much, I kind of want to show this high level animation from the PyTorchLightning open source repo. And again, what's really like, it's growing a lot of popularity. You can see it has about 10,400 stars, over about 1.2 thousand projects on GitHub are using it, and it's growing every day. So really good library. If you're developing PyTorch, you're not using Lightning, you should probably check out and try to start using it today. And what you can see here is on the left, we have this complex PyTorch code with multiple multiple data sets for train and test on MNIST. It has configurations for CUDA. It has its specific loop. And we can see here how we can minimize the code by converting it into a Lightning module. Now let's actually look at the Azure Machine Learning Studio. When we get started with Azure Machine Learning, this is the main screen that we see. We can see a lot of the different, keep track of a bunch of the different experiments of our compute events. There's also tutorials here and direct links to the documentation. There are a couple core concepts to get started with. The first core concept is the concept of our data set. So here we can create data sets from data stores, open web files, different open web data set repositories, also from local files as well. And we can register data stores directly from our other Azure data applications, whether that's Azure SQL, whether that's Synapse, and the data lake, or whether that's Databricks or Cosmos or queries on top of Cosmos DB. Once we have our data, and additional things that we can do here with our data is we can manage pipelines. So as our data is being uploaded, we can do jobs that can manage and these data sets and enable us to quickly iterate. The next core concept to look at is this concept of compute. And so what we have here, we have compute instances. I have here a compute instance running a GPU machine. If we get started here, we can see that we have all sorts of compute instances, very cheap compute with CPU, starting about like 18 cents per an hour. And again, these costs can be even less if you're using, if you're enterprise and you have those sort of enterprise agreements. And additionally, you can scale up to larger GPU machines with 48 cores and 4 GPUs and a terabyte of disk space and half a terabyte of memory. So you can imagine that this allows us to quickly iterate and develop compute that has pre-installed all the traditional machine learning packages, from Pandas to PyTorch to TensorFlow to pretty much any standard machine learning library that you would need. It comes pre-configured and pre-installed, including Jupyter servers and the rest. We can see also from when we create this compute, we can access it over SSH, Jupyter Lab, Jupyter, and also if you have Visual Studio Code installed, you can actually run your local code, Visual Studio Code, on your AzureML compute instance. So I'll pull that up right now. So you can connect these same compute instances that we're managing in the cloud, and we can actually debug and run the code that we have locally, as if we had it locally in our local Visual Studio environment. So here I'll put at the end I'll share this resource as well, and let's go back to our studio. So here I've set up a compute instance. One of the things that's interesting to note is while the compute instances themselves have their own disk and their own storage, we also have this concept of notebooks within Azure Machine Learning. So there's an entire notebook service built into Azure Machine Learning that can be connected to any one of your compute environments. And through that compute environment, you can persist your notebooks across different compute environments. So if we go, yes.
This is on your machine hard drive, this hierarchy, or is it for each of your machines?
So this is even better than that, and that's an amazing question, Saul. So what you're seeing here, actually, that this is in my Azure Machine Learning workspace. So everything that I have
shared across all of your machines.
Exactly. And if I want to create new machines, then I can access each of these notebooks and the notebook things that are stored in the notebook state across my different machines. So this is really valuable, for example, if I have a lot of data pre-processing and then I want to train a local model, instead of spending, you saw $4 or $5 an hour, or $2 or $3 an hour, even $1 an hour if I want to, or 30 or 40 cents an hour, depending on the machine. I can take a cheaper machine. I can do the processing I need on the cheaper machine. I can save my data. My data gets saved in my data sets. My notebook gets saved here. And then when I'm done, I delete that machine. I spin up a new machine, configure my environment, and now I can pick up exactly where I left off. The code's persistent. So, okay. So what we have here is our code. The way that I pulled this code, so this code is all open source and available in the official Azure Machine Learning Examples repository. And what you'll see here is if I want to get started, the way that I pulled this in is I just clicked clone on this code, and then I can just do git clone, and I can clone that repository locally. And if I want to pull updates to it, I can do, git pull, all the standard Git operations. Well, I need to actually be in the repo, but yes. So if I do Azure ML examples, and now I do git pull, I can pull any of the changes to from the global code. Everything here. I have shell, Ubuntu, everything. Yes.
Which machine is running this terminal?
What did you ask again?
Where do you select which machine is running the terminal?
So that's what's really cool about it. So here in the compute, the terminal is running from whatever machine that I have active. So here it's running on that same compute that I set before. But if I spun this down and wanted a simpler machine, I can do that as well. And because this remote directory is automatically mounted, anything that I pull down here gets automatically pulled down to my my file share. Okay, so let's actually start looking at some of these notebooks and see how we get started. So what I can do here is I have my Azure ML examples. I have some of the other examples from previous configurations as well. Here we have tutorials, and in tutorials we have using PyTorchLightning on Azure Machine Learning. So the first thing that we'll do is let's take a look at what it looks like to train a single node using the Azure Machine Learning service. So the first thing that we want to do here is to the first thing we want to set up here is to upgrade TensorBoard and make sure that we have Azure ML TensorBoard. We're actually going to use it at this stage, but later we will. And then the next thing we want to do is we want to connect our Azure ML workspace to our SDK. Tal, are you able to see my screen okay? I'm going to, just to make sure everyone at home, I'm going to maximize things a little bit better.
Getting fuzzy when you move around, but other than that.
All right, perfect. So now you guys should be able to see a little bit better. Let's set that at 150. Perfect. So here, the first call that we're going to do is we're going to pull from the Azure ML SDK that, again, we don't have to install because it's pre-configured on our Azure Compute instance. We're going to pull Workspace, and I'm going to do Workspace from config. And what this will do is this will attach the my current workspace, this entire Azure Machine Learning environment, to the running notebook. And then I just need to set up a couple configuration parameters. So the first thing is I need to define what the source directory for the job that I'm going to run is called. In this case, it's called source. And if you want to see where that comes from, we'll go in the standard mode. So it comes here from this file in using PyTorchLightning called source. We have our script name, which is our entry point, train.py, and we can actually open that up. So in train.py, this is the standard autocoder example from the PyTorchLightning examples repo. You can find the same thing here in PL examples, and we have that also. We have a version of that also here locally in our example. And what you have here is a Lightning autoencoder. Well, I'll quickly walk through kind of what this model is doing. So here it has two model components. The first is essentially a sequential feed-forward network with a ReLU activation function that goes into another linear classifier that essentially takes in our input, which in this case is an MNIST image. MNIST is the data set with all the different digits that are in 28 by 20, yeah, 28 by 28, I believe. And essentially what we have here is, so we have our encoder to encode it, and we have another model for decoding. The next thing that we have to implement is our forward function. This is how we actually inference our model. So here, what we do is, the first thing that we do is we take our embedding, we do self.encoder, and we return the embedding, and then this encodes our image into the embedding representation. Because remember, in our autoencoder, what we want to do is we want to take our input, we want to encode it into some representation, and when we're training, we then want to decode, and we want that to match the original thing. So that way, this encoding becomes a dense representation of our model that we can use for all those downstream tasks like clustering, image similarity, or features as well for other interesting machine learning tasks. And what's so cool about this PyTorchLightning is once you've developed your models using this interface, you can actually kind of reuse them and combine them because everything becomes a lot more standardized. So let's go back to our Azure Machine Learning service here. We have our training step here. So what we do is we get a batch from whatever data load we provide to the service, whatever data module. The batch is then split into the X values and the Y values. In an autoencoder, the Y value is actually going to be the comparing the decoded to the original image. So what we do is we encode the original image, we make our prediction using the decoder, and then we using mean squared error loss, we essentially compute the loss between the mean squared error of the image that we generated and the original image. And then the last thing we need to do is we need to configure the optimizer for backpropagation. In this case, we use standard Atom. And with that, we have all the components that we need to train our model. And what will happen is that PyTorchLightning will take care of the rest. So using the traditional data loader, we could also have data modules as well. More advanced concept that I'm happy to address in the questions. We create one for training, validation, and testing. And we'll see why in the next example here. We just initialize our model. We create the PyTorchLightning trainer from whatever parameters or configurations that the user passes in the terminal or in our Azure Machine Learning code. And then we can just train the model using trainer.fit. And PyTorchLightning takes care of the rest for us. Yes?
Can you show some examples of arguments?
Yeah, absolutely. So certain things would be like, for example, one of the cool features in PyTorchLightning is that it has early stopping. So one of the things that we could do is we could say we want, even though there's early stopping, we want to make sure that we have a max amount of epochs so that we don't go more than 60 epochs or 80 epochs. Additionally, we can do the opposite too. Is even if there's early stopping, we might want to encourage our model to continue to train beyond the early stopping. So we could put a min number of epochs. We could play around with our batch size, the number of images that we evaluate against before we calculate the loss and backprop again our loss to update our parameters, we can configure that as well. And there are many other features in addition to distributed training that we'll see in just a minute. So this is our training script. Let's actually go back to our training notebook and actually show how we can train. Now look at how we train this script with the Azure Machine Learning Service. So the next thing that we need is an environmental configuration. This configuration file here, environment, is a simple YAML file that essentially just gives us all our pip dependencies. So we want to use the Azure ML defaults. We want to use PyTorch, Torch Vision, which we're using to load our MNIST files, ML Flow and Azure ML Flow, which is going to be used for the logging. And here we can configure PyTorchLightning as well. And so this way, when we submit to our cluster and our node for training, it's going to have all the environmental dependencies that we need to train our PyTorchLightning model. We just provide a name for the environment, a name for the experiment that we want to run, and a compute cluster. So we can actually create the compute cluster through the SDK, or we can actually, if you look here, we can create our compute clusters in our compute section of the terminal, and we can say how many cores, whether we want the cluster auto scale or not, what's the minimum amount of images, the max amount of images, whether they're dedicated or low priority. If we're using low priority images, we actually can save on costs by an order of magnitude of costs. And this is actually one of the few services left that provides that functionality. So it's a big competitive advantage for Azure Machine Learning that you can use low priority instances to reduce your costs when doing distributed training. Okay, let's go back to, in this case, I have a cluster here with, it can scale up to 2 nodes. Right now it's idle with 0 nodes. It's called V100, and it has 2 NVIDIA Tesla K80 GPUs. So let's go back to our notebook and actually show how we submit a job to that cluster. Any questions up to this point, Tal?
No.
All right, perfect. So what we do is we load our environment, and what's really cool here is the base image that we use for training can be any Docker environment that we configure. Azure ML actually provides some standard base images based on Ubuntu that you can use as your base image for training. But technically, any environment, if you have much more complex code with with your own DLLs or your own custom plugins, you can create your own base image environment, and the cluster will scale using that environment. So in this case, we're just going to use the standard CUDA 10.2 Ubuntu image with OpenMPI, which allows us to scale and communicate across our cluster. And now we're going to configure our training job. So what we do here is using AzureML.core, we import experiment and script core config. Here we pass the source directory, our train.py script name, and here we're going to give in our arguments. So for our first job, we're just going to run it on 1 GPU of our cluster, and we're going to do a max epochs of 25, and then we just give our compute target. So this could be our cluster, this could be actually the local machine that we're running on, or even this local VM that we're running on as well. And we provide our environment to get things set up, and then we can submit and run this job. So I've actually done this earlier, and to save on time so you're not waiting for me to run the job, let's actually take a look at what happens. So I can click on this in the experiments view of Azure Machine Learning. What I can see here is I can see that the job completed. I can see all the metadata of the job, everything from what version of the samples I used, the environment. I can see that running this job on one node took about 6 minutes to run. Additionally, what's really cool is I have a snapshot as well. So if something did fail or I wanted to do debugging, I have a snapshot of all the code in my environment that I can go and I can compare and start figuring out. And there's also additional Azure ML APIs that we won't get into here, but that you can also integrate with also through ML Flow that can help with explanations, fairness, and interpretability on my models as well.
Can you show the logs?
Yes. So here I can see all the driver logs, and what's cool is when you're actually running the model, you can see these logs come across in real time as well, as if you're developing on your own machine. But you can see all the logs from building your image, all the internal AzureML processes, as well as the AzureML logs. And what's really cool here, and we're going to see it in just a minute, is you can actually integrate with these logs with TensorBoard for debugging. And because PyTorchLightning has a very simple interface for integrating with TensorBoard, we can do it with barely modifying our code. So let's come back to that in 1 second. What I want to show you quickly now is why it's so powerful that we're using PyTorchLightning. Because now I can take the exact same environment that I did before that took 5 minutes, and I can just change one thing. I can change from that one where we used 1 GPU to 2 GPUs, and without changing any of my training script or configuration, I can take advantage of the fact that each node on my cluster has 2 GPUs. And you can see now when I click to the second run here for this exact same job, you'll see that it takes almost half the time. So here it took only 3 minutes and 24 seconds to train versus the 6 minutes that it took for the first job. So significant. And what's really cool is if we were doing this in PyTorch, we would have to manage the ranks, and we would have to import VOD, and we'd have to do like a lot of custom configuration in order to get this working. And then later, when we wanted to run across multiple nodes, we'd have to do even more configuration to this code again. And what's even crazier about that is, let's say we had another piece of code that somebody else ran that only runs on 1 GPU. If we want to now combine it with our code, we now have all this boilerplate code that complicates things. So this really simplifies a lot of the training process and environment.
Ari, how can I modify what kind of a strategy I use in order to consolidate the different weights on different nodes?
Absolutely. So you can actually, in the PyTorch Lightning, you can actually override a lot of the different hooks. So if I go to the PyTorch Lightning documentation here, we can actually see we have our trainer. Sorry, 1 second. Let's go to our trainer. And what you can see here is, while you have the standard training flags, you can actually override things, override additional flags here. Let me see if I can find the perfect example from the documentation for you. 1 second. I thought it was on this page, but I'll pull it up for you. If I can't find it right in this moment, I'll link it in the end. But we can actually take a look at our code, at the code here in the PyTorch Lightning example. So we go to the basic examples. We can see our simple image classifier, and you see here how we have each of these hooks, like forward, training steps, and your configure optimizers. So we can actually override each of these functions and the functions that they use. So for instance, if we wanted to change how we do a forward step or a back step, we can override those functions. And by doing that at the PyTorch Lightning level, it automatically transfers to the Azure Machine Learning level. Does that answer the question?
Yes.
All right, perfect. So one of the things that I want to note now is, as you saw here, there's this field for metrics when we're running our jobs. As you can see that this metric field is empty. Part of this is because in the code that we wrote here, which is just boilerplate code, we didn't do any logging. And so now I'm going to show how, using MLflow or TensorBoard, we can actually integrate logging to get a better sense of what's going on as we're training our model. So the first thing that I want to show is logging with TensorBoard and what that looks like. So here, for example, we do the same thing that I did before, and this time we're going to use a different training script. We're going to use trained with TensorBoard logging. Let's take a look at this script. So in this script here, the training with TensorBoard logging, the only major change that we have here is we can access self.log, and now we're going to log our loss at each of the training steps. If I want to do this for validation steps, or if I want to do this for testing, I can override those events as well. And we just add an argument for the log directory, which in Azure gets defaulted to .logs. And here, what we do is we just create a TensorBoard logger. We provide the log directory, which is going to default to where Azure stores its logs. And then what you can see is actually when I'm training my job, I actually, through Azure on the actual compute instance that I'm training, we'll actually be able to see the loss, how it decreases as the model trains, and we can also get access to all the debugging tools of TensorBoard in this way. And we can log anything we want. So this helps us to use TensorBoard. What we might also want to do is to log directly into Azure Machine Learning as well, because if we do that, it gives us a lot of advantages that we can use things like the hyperdrive API as part of the Azure ML SDK that allows us to, in a distributed manner, optimize our hyperparameters. Though we can also do that with PyTorchLightning as well. And we can also visualize all the performance and metrics across multiple jobs in this way. So the way that we do that, and I'll quickly show that, is very similar to what we did before. We'll use the MLflow logger. Azure Machine Learning has native support for logging with MLflow. And all we need to do here is we just initialize MLflow logger. We get the MLflow URI of our experiment that we're running through the run context from Azure ML in the workspace. We pass that to the MLflow logger, and now all the same logging operations that I did when I logged on TensorBoard will now log through MLflow, and I can visualize them with MLflow. And one of the coolest things with PyTorchLightning is you can actually stack loggers. So when I provide loggers here, I can provide the MLflow logger, but if I wanted to in the future, I can actually do this, and I could initialize a TensorBoard logger, and in this way, I would see the logging in both environments simultaneously. So what does this provide? Well, when we actually go here in our third notebook example, and we log with MLflow, we don't have to change anything specific here. But when we actually run this job to log with MLflow, what you'll see when I actually view the job that I ran is that we get all our metrics, and we can actually see the loss in the experiment environment. So if I go to the metrics here, I can actually see for each epoch how much time each epoch took. I can see how the loss changed over time. And if I actually go to the specific experiment, if I'm running multiple iterations or changes of my code, I can actually see all of them and visualize and compare work that's being done by multiple data scientists or machine learning engineers working on the same project. Additionally, if I'm using the hyperdrive, I can actually use and attach to these same metrics that I'm logging to optimize my hyperparameters. So the last really cool thing that I want to show here is we talked about how we could optimize. We talked about how we can optimize for training across both GPUs on one node, but we can actually use this exact same code to train across multiple nodes. We only have to make one minor modification in order to do this, and I'm going to show you how to make that minor modification now. Essentially, what we have to do in our train script, we just need to register the train script to recognize that it's being run on an Azure ML compute cluster. And in this way, PyTorchLightning will know that it's being run on Azure ML. So we register all our standard environmental variables. And then we can access, these by in our multi-node example here. And again, everything here, we just call set environmental variables. We just provide how many nodes that we have, And in the same way, and that's all we need to do. And now this script will distribute across as many nodes that we provided. So in our actual training script now, what we can do is when we create the same configuration to submit the job, before we say how many GPUs, how many nodes, in this case 2 nodes, and when we run this job, we'll see that this job takes even less time than the job that ran on 1 node to train. So that kind of sums up everything here. What I am going to do at this point, Tal, is do you have any remaining questions? Or if there are additional questions from the chat, I'm happy to answer any of those as well. But I think to just one last thing here is to sum up is that I hope that you get a sense here of the power of Azure Machine Learning as a platform for managing experiments, for training, for managing compute, and also the power of PyTorchLightning as a wrapper on top of PyTorch to essentially hypercharge the power of PyTorch on Azure Machine Learning. Perfect.
Oh no, I said hello and I was on mute. I never learn. I never learn.
No worries. So Adam, welcome back. Do we have any questions coming in through the chat?
What we actually had was some questions about where they will find some of these things. So I tried to bring up some more of the links, and I shared some of them on Twitch and some of those other places as well.
Absolutely. One of the things that I want to provide here, I'll pull it up as well right now. If you want, I am available on Twitter, and I monitor my Twitter pretty closely at PythicCoder. And so if you have additional questions or additional asks for resources, feel free to tweet at me as well. And again, we'll make sure that everything that we talked about today, all the links have been provided with Adam, so you should be able to access them as well. I also, additionally, everything we discussed today, I wrote into a 3-post Medium series on our Azure Machine Learning, on our Microsoft Azure developer blog. And I also there's a lot of really good content there. So if you're interested in machine learning, you're interested in Azure, keep an eye out on our Microsoft Azure developer blog.
That's absolutely amazing. And I put all of the links on, let me just rearrange that so that I'm not covering anyone's face up with that link. So I put all of the links on that website later on today. And, of course, there's you on your Twitter handle on there, and of course I will share mine as well. I also reshare the stuff on there as well too. So it's really great. The other thing I wanted to just highlight is for people who are absolute beginners to Azure machine learning. There's lots of options, and I think we said in the Developer's Guide to AI earlier in the week that there's some really good documentation, and also there's learning paths as well. So I brought this link up before, but all of the Azure machine learning docs are here. But if you aren't sure really where to start, then maybe try the learning path. And this is one of them. This is actually an intermediate. This is an intermediate learning path, the link that I brought up. But if you go to that link anyway, and then just have a little look around, you can actually sort of browse the paths on the Microsoft Learn site, and you can say, well, for example, I'm a data scientist and I'm looking for an introduction to Azure, and you can say I'm, a beginner, intermediate, advanced, or perhaps you're watching today and you're not a data scientist, you're a developer or even an IT professional, and you're just looking for some more information. Have a browse around, use that as a basis for where to start, and you should be able to find something. I mean, there's so many great resources on there. We've had some. Another, not related to today's content, but I remember we worked with Oxford University to put together a whole learning path on becoming an AI edge engineer. So it's a completely different thing that we're talking about today, but just some really great collaborations to build this content up as well. And of course, I can't forget, Ari, your wonderful articles as well, which there will be in the resource page. So thank you for sharing all of those with us as well. And Tal, I'm the same, goes for you. If you want to share, any of your links or resources, we will put them on the website later on, and we've actually on there as well as also links where they can find you online as well. So cool.
One last thing I wanted to call out as well, because it actually just got tweeted in the past day, is on the PyTorchLightning page, there actually is a whole new thing here highlighting some of the most popular projects that are using PyTorchLightning. And so you can actually get started or look at how other people are taking advantage of PyTorchLightning and now using and you can see actually the Microsoft research team around FastFormers is using it as well. I was reached out at one point by the HoloLens team that's really interested in this content as well. So what's really cool is you can take a look at these examples, and using the resources that I showed earlier, you can actually take these projects and now run them in Azure Machine Learning as well. One last thing too is there's also a really cool project called PyTorchLightning Bolts, and this is essentially kind of like a library, a toolbox of many different types of model implementations, as well as custom transforms. They have all sorts of things across GANs, detection, autoencoders, regression, reinforcement learning, and computer vision, you name it. So also really worth taking a look at. I'll make sure to put those in the chat and so that they get sent out as well.
There we go. I hope I've typed that in without making any mistakes.
Well,
but there is the link.
Perfect.
Wonderful. Just one thing. I mean, you did mention that we can talk quite a lot about these features. If you don't have Azure, like, what does this actually cost to use things like use the Azure ML Studio? Is there a heavy cost to that? How much?
Sorry. Go ahead.
No, I was saying, how much can maybe a casual user expect to spend on that sort of thing?
So it's kind of hard to estimate these things off the top of my head, because it depends how much you use or what you use. It really is like a pay-to-play type thing. That being said, like, you could see, like, when we looked at the compute resources here, you can get started with even some simple GPU models for just for about $1 an hour. You need to be careful because that adds up. But even on the CPU side, 18 cents. And what's really nice here, and I would also recommend, we have links here in the blog post as well. If you're new to Azure, you can get started with a free account, $100 of credits, which is more than enough to get started playing around and familiarizing yourself with these concepts to see whether Azure Machine Learning is the right fit for you.
And so it's sort of the age-old best practice. When you're done with it, turn it off.
Yes, absolutely. And brilliant. If you're, but like, again, if you're in a larger organization that's managing this, they also have monitors that you can add to monitor resource usage and consumption, and that can integrate into this. You can set core limits to make sure that people don't get crazy or too wild. There are some protections in place to keep costs in check. But again, if you're interested in scaling out like a good data science team, it's really worth taking a look at a lot of these tools. They're really interesting. And I think that PyTorchLightning really does help you supercharge a lot of your traditional PyTorch flow.
Yeah, and I guess sort of, if you do have a very large organization, there are all of those sort of ways of making sure you keep control. And there was something like Cloudine, I think it is, which you can use to sort of analyze that as well. If you've got a really big environment, that's another Israeli company, isn't it?
It is an Israeli company that was purchased by Microsoft and integrated into everything. So
we had very good taste. Cool. Well, a huge thank you to both of you, Ari and Tal. And as I say, once again, we will put those links and resources as well. And if you want to find out more about Ari or Tal, then go over to that site as well. It's got their profiles and links to find them. I just wanted to mention a couple of things actually before we go, though, because we've got some exciting things coming up in the next few days. So as I mentioned, we had the Tech Days AI event, and that was on Tuesday, and we are actually going to have another Tech Days for security. And actually, we don't have the site up about this yet, but if you go to this link tomorrow, hopefully you'll be able to register for that security event for that. So that's for folks that maybe aren't familiar with cloud security but are looking for some more information. And the other big thing that we've got coming up is, I don't know about you, but I've noticed it's getting pretty cold, and you probably haven't noticed in over in Israel, but I'm sort of feeling a bit like it's like this right now. It's not really, but you know, it is that time of year where many people, depending on where you are in the world, have different sort of festive traditions, holidays. It's Thanksgiving over in the US. A lot of folks around the world will be celebrating Christmas and Hanukkah coming up, and so for a lot of people, they like to sort of end the calendar year with you know, some sort of celebration, and it's a bit difficult this year because we can't all, you know, sort of go and see our loved ones the same way that we would do in the past. But one of the things that our tech community is doing is something called the Festive Tech Calendar. And this is going to run from the 1st till the 31st of December. And it's going to be every day. There's going to be a few different things revealed. There's going to be a few different things behind the door each day. Each day at 10 a.m. UK time, that's 12 o'clock Israel time, you get to open the door and see what the surprise is. So we have a launch show with yours truly and also a few other guests on Tuesday at 10 a.m. GMT. That's 12 o'clock Israel time, 11 a.m. for Central European time. And if you go to this website, aka.ms/festive, that will take you to Learn TV, and that's where that will be transmitted. So please join us on Learn TV on Tuesday. And also, if you go to this website, festivetechcalendar.com, they're going to have every day. They actually have the calendar already up, but and who's going to be presenting things, but actually what's behind each door, that's still a surprise. So that's going to be fun. And we've got to have something a little bit festive because, you know, I'm missing all of the traditions, and actually I miss coming over to like Israel. I came a few times last year, and they had those little donuts for Hanukkah, which I really quite liked as well. So it's always about food with me. But at least we can have some fun online this year, and I'm really looking forward to that series. So I think that's about it, and that's really about all we've got time for, really. Because we're soon out of time. We've got about a minute left before the program ends. So just to say thanks again to both of you. And don't forget that you can join us 24 hours a day on Microsoft's Learn TV site, aka.ms/cs-Learn TV 24/7. But until next time, it's bye from me and Ari and Tal, and thank you very much for joining us.
Thank you for having us.
See you next time.
See ya.